Hello everyone, in this video we are going to explore how the crystal field theory helps us understand the colors of the coordination complexes. The way how colors are perceived for coordination complexes are through subtractive mixing, meaning that when a white light interacts with an object, the object will absorb some of the light, then reflects or transmits the rest of the light, which contacts the eye. The object is perceived as whichever color that is not absorbed. For instance, looking at a solution of a hexa-aqua titanium 3 complex, we can see that the absorption spectrum of this ion absorbs strongly between 490 and 580 nanometers, the green-yellow region of the visible spectrum. Referencing to the color wheel, we can see that purple is the complementary color of green and yellow. Therefore, the color of this hexa-aqua titanium 3 complex appears purple to our eyes. For coordination complexes, the repulsions between electron pairs in the ligands and any potential electrons in the d orbital results in an increase in the energies of the d orbitals. Depending on the degree of repulsion, the energies of each d orbitals increases differently. The differences in energy between these split d orbitals is known as the crystal field splitting energy. In a strong field complex, the splitting is large, and in a weak field complex, the splitting is small. Electrons need to absorb enough energy to go from a lower energy d orbital to a higher energy d orbital. The energy of a photon is associated with the wavelength of a photon. For a lot of the coordination complexes, this wavelength is in the visible spectrum, and this is why we can associate the size of the crystal field splitting with the color we see. The magnitude of a crystal field splitting in a coordination complex depends in large part on the ligands attached to the central metal. The spectrochemical series arrange selected ligands from strong field to weak field. A strong field ligand is associated with a large value of crystal splitting energy, and since the energy is indirectly proportional to the wavelength, we can expect strong field complexes to absorb photons of lower wavelength. In this case, the complex ion hexacyanoiron 3 appears to be a deep red solution because it absorbs light of lower wavelength. On the other hand, a weak field ligand is associated with a small value of crystal field splitting energy. For the complex ion hexaamine nickel 2, it appears blue as it absorbs photons of lower energy and higher wavelength. In summary, transition metals tend to form complex ions. The complex ion contain a central metal ion bound to one or more ligands. These ligands have strong field and weak field properties that can affect the size of the crystal field splitting energy for a metal ion. The crystal field splitting is a result of the metal ion d orbitals having different energies due to the degree of electron repulsion. The size of the crystal field splitting for the metal ion determines the wavelength of the photon it absorbs and the color of the complex we see. Thank you for watching this video. If you have any questions, please feel free to reach out.